Hello everyone, welcome back to Bytes of CSC. So in this lecture, we'll be talking about the greedy algorithm. Now, we need an algorithm to solve a real world problem. And there are different approaches to solve a real world problem, and depending upon your kind of approach, an algorithm can be divided or can be distinguished into different categories like the divide and conquer or dynamic or greedy. Now today we'll be talking about greedy algorithm, and also we'll be going through a type of greedy algorithm which is the Kruskal's algorithm. Say we have two games which we are playing, that is, one is chess and another is Scrabble. I'm sure all of you know what a chess game is like. Even if you don't know how to play it, you have an idea like what a chess game is like, right? And in Scrabble, well, you will be given some letters and you will have to find out a meaningful word out of those letters. Now, from my explanation, one thing is very clear, that the approach to solve a chess game is not the same as the approach to solve a Scrabble game. In chess game, in each of your turn, the kind of move you take will determine if you will win or lose the game. So you may say that chess needs a very calculated move, whereas in case of Scrabble, you don't really need a calculated move to win. So the problems where a calculated move is needed to solve the game, that can be solved using a greedy approach. Why? Because a greedy algorithm or a greedy approach, it builds up a solution piece by piece by choosing the next piece that offers the most obvious and immediate benefit. So in this case, you might say that turn by turn, it chooses the best move that will ultimately help you win the game. If we look into a more practical problem, like say you have 6 computers and you have to maintain a network among them, that is, you're linking these 6 computers together, and every link has certain maintenance cost. So even if you want to link the computers, you have to keep you are also keeping in mind the budget to maintain those links, and you need the kind of links that will cost you least. So this is, in graph approach, is known as the minimum spanning tree, where all the nodes are selected, but only those edges are selected which costs the least. So one approach to solve this minimum spanning tree is by using a Kruskal's algorithm. So let's see how a Kruskal's algorithm works. So here you have a graph of 6 nodes, and every node has an edge cost every edge has an edge cost associated with each. So the first thing you have to do is to sort the edges in ascending order of weights. Now the least cost edge is 1 that exists between B and C. So you include that. Next is the edge weight 2. That there are 2 edges with edge weight 2, that is BD and CD. So you add 2 edges and you also record the edge weight. The next higher weight is edge weight 3 that exists between C and F. So you include that. The next higher edge weight is edge weight 4, and there are 3 edges that contains that has edge weight 4, that is AD, EF and DF. So you include that. And then the next higher cost is edge weight 5, and that exists between C and E and also between A and B. So you list that. And the highest cost edge weight A and C is added to this list. Now you have to repeatedly add the next lightest edge that does not produce a cycle. This is very important. Why? I'll come next. Okay, so let's get started. So first we add edge CB. This is the edge. Next, you have to next category, that is of edge weight 2. We have two edges, CD and BD. So let's add CD. Now before you add BD, you have to check that if you add BD, it does not produce a cycle. A cycle is like this. Say ABD is a cycle. These three nodes are connected to each other and this also forms a cycle. Again, ABDC is also a cycle. So now if you add B and D, if you add BD, that is going to form a cycle. So definitely you cannot add BD. So you move on to the next level. In the next level, we have this HCF, that is this one. This is also not forming a cycle, so you add that. Okay. Now, at this level, you have three edges, AD, DF and EF. Now let's see what the spanning tree looks like. This is your spanning tree. Now if you try to add edge AD, well, you can add it because it is not forming any cycle. This is your edge AD. So AD is included. Now if you try to add edge DF, this is your DF. So this is going to form a cycle. CDF. This is going to form a cycle. So you cannot include DF. Now if you try to incorporate EF, this is your EF. Yes, EF can be included and EF also does not form any cycle. So this is what you have got till now, and this is how your spanning tree looks like. Now see, all the vertices have been added to this spanning tree, that is the minimal tree or the minimal graph you have found out using Kruskal's algorithm. Now you don't have to look any further, that you don't have to consider these levels, because you are interested in adding all the nodes but not all the edges. Now what is the problem with this kind of an explanation that I gave you just now? Now when we were stuck at this point, we saw that this tree looks like this, and then we just visually went through the graph and we found out that what is adding which edge is going to form a cycle, and we just discarded those edges. But how are you going to make your computer understand that? So let's delve a little deeper into the Kruskal's algorithm. So basically we are trying to check if there is a cycle in a Kruskal's algorithm going the algorithmic way. So your first move will be to make a set of vertices. So this will be a disjoint set of vertices, that is A, B, C, D, E and F. So there are 6 sets for each of your vertices. So then you start adding the edges which you have found out and sort it in ascending order. So first you will be adding edge C and B. So what you do is you put these nodes C and B into one single set like this. The others will be left as it is. So BC, it belongs to the similar set. The next edges are CD and BD. So you include CD same. So C was already there, so you have picked up D from this set and you have added to this set. Now your set contains B, C and D. Now when you will be adding or trying to add BD, you will have to check if B and D, they already belong to the same set. So what it means is, if they belong to the same set, it means that there is already a path that exists between B and D That is, in this case, we had till now added BC and CD. So the path from B to D in this current diagram will be D, C and B. Now if you add another edge, that is, if you are trying to add this BD again, that will mean that you are getting a cycle. You are adding another path and that is going to form a cycle. So we don't add BD. Next we will check for the next node, that is C and F. Now C belongs to this set and F belongs to this set. So you can surely add B, C, D and F. That is, you can add this H, CF safely into your minimum spanning tree. Now next you have AD, DF and EF. Now A belongs to this set, A and D belongs to this set. So A and D, they don't belong to the same set. So you can safely add A to this set. Now D and F, they already belong to the same set. So you cannot add D and F. Next you have to check F and E. So F and E, again, they do not belong to the same set. So you can always include this edge. So now it looks like this. And see, you do not have any lone node that is present here. There is no singleton set that contains an edge. That contains a node. So you can safely conclude that your Kruskal's algorithm or the minimum spanning tree has been found out and all the nodes have been included. So now if you go through the procedure, or this is the algorithm, not really a program, that how Kruskal's algorithm is carried out. So you have an input which contains a connected undirected graph GVE. So this is your graph G with edge weights WE. So 5, 4, 3, 2, these are your edge weights WE. And you have to output a minimum spanning tree defined by edges X. Now for all for all U, that is node that belongs to the V, means the vertices, you make set U. So your make set U is this one, the first step of the previous slide, A, B, C, D, E, F. Now you take a set X, which is an empty set. So we'll be looking into X later. Next, what? You sort the edges E by weight. This is what you have done. So actually, see, what I am doing in this step is I am going through all what I have done up till now, and I am just connecting those pieces and showing you how the entire algorithm is working. So this is the sort the edges E by weight. This is your that step. Next, for all edges UV, that is edge between U and V that belongs to E. E means the set of edges in increasing order of weight. If find U not equals to find V, this means that if U and V, they do not belong to the same set. Find U means find the set where U belongs, and find V means find the set where your edge V belongs. And you have to see that these two nodes do not belong to the same set. So if they do not belong to the same set, add edge UV to X. So this is your add edge add edge UV to X and union UV. So this is where the union thing has been done. So first BC was added, then BCD, then BCDF, then ABCDEF. And this adding edge UV to X, so this is that X. that we have done 2 slides before when I first started and making you understand how the Kruskal's algorithm works. So X is when you added BC, so CB was added first, then CD was added. So this was that empty set X at this level, and you were adding edges one by one to that set. And finally, when you work out these edges, you get this minimum spanning tree, that is this one. This is your final result, which is also the output. So this is your input, this is your output, this is your mix set. Let me just say this is your mix set. So this is your sorting. This is step number, say, 2. This is your sorting part. So for all edges, this and this. This is your union UV. This is your union UV. And adding edge X to, adding edge UV to X, this is your step. This is the final X that you have got. And this is finally your output. This is the whole walkthrough of your Kruskal's algorithm. Now, if you have to know that what is the runtime complexity of Kruskal's algorithm, so for a height balanced tree, if you use a height balanced tree as your data structure to find out that union and find set and make set, your Kruskal's algorithm will have a runtime of O E log V. Now, if you ask me what is a height balanced tree or why is it E log V, I will be explaining that in a separate video. I do not want to make this video too long. It's already very long by this time, I think, and I don't want to make it too informative or too boring for you. So just know this information for now. I have completed the Kruskal's algorithm, the explanation of the Kruskal's algorithm, and I will be doing a separate video on height balanced tree, and from there I will make you understand that why it was OE log V. For now, you just know this piece of information. So that is all about Kruskal's algorithm for now. So thank you for watching, and if you liked my video, please give me a thumbs up and share it with your friends. Goodbye.